Okay, a biconvex lens is made of glass with refractive index 1.52, having the radii of curvature of 20 cm respectively. Calculate the focal length of the lens in water or in carbon disulfide. Okay, so he give you here refractive index of the water 1.33 and refractive index of the carbon disulfide 1.63. Okay, good. So these are the medium. Yeah, what I can say is these are the medium. These given here are all refractive index of the medium. Whereas here he give you 1.52. This is refractive index of the glass for the lens. So this is the refractive index of the material. Yeah, this is the refractive index of the glass or the material. Okay, it is a biconvex lens. Okay, let's draw a biconvex lens. So biconvex lens is convex at both surfaces. Yeah, that means from this side is convex. From the other side, we look also convex. This biconvex lens. Okay, let's color our biconvex lens. Okay, good. So we have radii of curvature for each of the surface. This is the R. Okay, we have the radii of curvature R, both R1 and R2. Okay, the 20 centimeter. Because this is a biconvex lens, both surface have the same radius, 20 centimeter. So R1 and R2 both are 20 centimeter. And then he asks you to find the focal length of the lens. So he asks for focal length. Okay, for two different medium. Okay, so okay, let's do it. Yeah. All right. So this is our lens. Okay. This is our lens. Now let's look at the medium of water. Okay. Now let's look at if the medium is water. So the refractive index of the medium is 1.33. Okay. So to find the focal length of thin lens, we use the Lensmaker equation. Don't use focal length of lens is R/2. No, yeah, this is wrong. This is for mirror. Mirror only has one surface, so it has only one radius. But thin lens, it has two surface. Okay, so mirror only has one surface, only has one radius, so use R/2. But we're not going to use this for lens. Yeah. So thin lens, we're going to use this formula. 1/f equal to which is called the Lensmaker equation. Okay, Lensmaker equation, which is this one. Yeah, Lensmaker's equation. Okay, the formula is okay, so what's the formula? The formula is 1/f equal to n material over n of the medium minus 1, and then 1/R1 minus 1/R2. Be careful, it is 1 minus 2, not 2 minus 1. Yeah. Okay, so look at this one. This is for thin lens lah. This to find thin lens, the focal length of thin lens, we use this formula because it has two surface, two radius, R1 and R2, whereas mirror only has one radius. That's why it's just a very simple R over 2. Okay, for thin lens you cannot use R over 2. You must use 1 over R1 minus 1 over R2 and the whole Lensmaker equation. Okay, so right now we need to know the R1 is positive or negative. The R1 and R2, whether they are positive or negative. So that one you need to draw a ray diagram. Draw a ray diagram. Let's determine together. Okay, so okay, I draw ray diagram over here. A simple ray diagram, not a complicated one. Okay, let's do it. Yeah, so okay, it's here. Okay, so now put our object over here at one side. Put our object at one side. Okay, now we need to draw the okay, now we are using water. Okay, that means this one is the glass, the lens, the glass lens, and then outside is the water. Okay, water is the medium. Okay, now first of all you must draw the incident ray and refracted ray. Draw the incident ray, and then refracted ray. So for lens, the light can pass through. Okay, remember, for thin lens, the light can pass through. Yeah, refraction, the light pass through, the light passes through. Okay, this is very important. And then we're going to know. Okay, we're going to check the radius. Because we know the R1 and R2 both are 20 centimeter. But is it positive 20 or is it negative 20? And then which one is the first surface? Which one is the second surface? So which one is first surface? The one that the incident ray comes, the light first enter, that one is the first surface. And then the surface where the refracted ray exceed is the second surface. So if the light enters from the left and then come up from the right, so the left is the first surface, and then the one to the right is the second surface. Okay, and then okay, let's draw our R1 and R2. Yeah? Let's draw our R1 and R2 to determine the position of R1 and R2. Okay, so now let's draw. Okay, let's draw our R1 radius for surface 1. So radius for surface 1, this is our surface 1. See or not? This is our surface 1. So our R1 is over here, because the center of curvature. Okay, never mind. So this is our surface 1. So our radius or our center curvature is over here. Center curvature 1 is over here. Okay, center curvature 1 is over here. So the center curvature 1 is same side with the refracted ray, or we can say the radius. Let's look at the radius. Radius is over here. This is the R1 radius for surface 1. So I want to ask you, is this radius 1 positive or negative? Should we put positive value for R1 or negative value for R1? Is it positive 20 or negative 20? How to know? We need to check the comparison partner. This one, okay. I think previous example I already see this one. Okay, I want to rewrite this into here. Okay, rewrite this one into here, over here. Okay. So remember the comparison partner, yeah? The comparison partner, the object distance always compare with incident ray, but the rest like image distance and the radius all compare with refracted ray. If same side positive, real. If opposite side is negative, virtual. Okay. So okay, I write down over here already. So the radius compare with refracted ray. So that's why you need to draw your incident ray and refracted ray first. Then you can compare the refracted ray with radius. So this radius one is same side. Is same side with the refracted ray. So this radius one is positive because same side. So it is positive. Understand? This radius one is positive because same side as the refracted ray. Okay, same side. And then how about the second surface? Let's draw the second surface. This is our second surface. And where is the center curvature? Center curvature is over this side. Center curvature 2. So the radius of the second surface is 2 to the left hand side. The radius of the second surface is to the left hand side. This is the radius 2. Now this radius 2, is it positive or negative? Radius compare with who? Radius compare with refracted ray. Just like the image distance, the radius also compare with refracted ray. So this radius is opposite side of refracted ray, not at the same side. Yeah, this radius 2 is not at the same side with refracted ray. So they are at the opposite side. Refracted ray is at the right hand side, but radius 2 is at the left hand side. So facing left hand side. So this radius 2 is opposite side of refracted ray, not at the same side of refracted ray. So this radius 2 is negative because opposite side, when radius and refracted ray opposite side, is negative. Understand? This radius 2 is negative because not at the same side with the refracted ray. Okay, so now we know that this R1 is positive 20, R2 is negative 20. That's the way you need to write. Okay, so now okay, write down material. Okay, refractive index of the material is 1.52. Refractive index of the material is 1.52. Okay, that's the lens. All right, that means the material, that means this is for the lens, the glass lens, and the medium is the water lah. Yeah, the material is the glass lens lah. Understand? So refractive index for material is the glass lens. So 1.52, and then for the medium, the refractive index is the water. For the water is 1.33. I just put 1.33. So minus 1, and then 1 over R1. R1 is positive. That one is positive 20 centimeter. Positive 20. Positive 20 centimeter. Okay, whereas and then minus R2. R2 is negative. R2 is negative. So put the value negative 20. Negative 20 centimeter. The centimeter unit you need to write together with the value because it is not an SI unit. So you must substitute together the unit centimeter so that you remember that focal length also centimeter. Understand? And the sign positive, negative, very important. Yeah, when we substitute the value. Okay, so let's calculate and check what's the value of focal length. Okay, check the value of focal length. First get the 1 over f. Then so okay, this is 1.52. This one minus 1. I mean can simplify this first. I think we can simplify this first. 1.52 divide by 1.33, and then minus 1. You will get 1 over 7. Yeah, here you get 1 over 7. And then how about this one? This is 1 over 20. Is 1 over 20, and then negative, negative, positive, positive, positive 1 over 20. Okay, negative, negative, positive. So okay, and then calculate 1 over f is equal to so 1 over 20 plus 1 over 20, okay, and then multiply by 1 over 7, okay, then this is 1 over 70. So don't forget to take the reciprocal. Don't forget to take the reciprocal, because this is the 1 over f, not f. Understand? This is 1 over f, not f. So you need to take the reciprocal. So it is 70. So you get this is f is positive or negative? Positive or negative f? I got positive 70 centimeter. So okay, I got positive value for the focal length when put in the water. So this proves that the positive sign of focal length shows what? What is mean by positive f for lens? When f is positive, it's converging lens. So when put in the water, it is a converging lens. Understand? The positive f means it is a converging lens. Okay, now how about okay, am I right? Yeah, positive 70, that's correct. So this is correct. Yeah, converging lens. Now how about putting it in carbon disulfide? Okay, so now question B. So this one I want to put over this side lah, at the top here. Okay, now I want to do question B. Yeah, question B. Now I put in the carbon disulfide. With refractive index of the carbon disulfide is 1.63. So now this is the medium lah. This is the refractive index of the medium, the new one. Okay, the new one. Okay. The material is still the glass lens, 1.52. So I think the rest setup is still the same. R1 still positive, R2 still negative. Yeah, follow the same setup. The only thing different now is the water medium has become carbon disulfide. Yeah. I can draw how to draw. How to draw. Yeah, maybe just draw it over here a little bit. Okay. Yeah, so it still follow the same, just that now the medium has become carbon disulfide. I put the lens inside the carbon disulfide. What will happen to the focal length? Yeah, if I put the glass lens into the carbon disulfide medium, the rest is still the same. Yeah? R1 still positive, R2 still negative, because compare with refracted ray. Yeah, same side positive, opposite side negative. So okay, I still use the same formula. Yeah, this Lensmaker equation, and I substitute the value 1 over. Okay, let's calculate. Yeah, substitute the value 1 over f equal to. So yeah, this material is still the glass lens, 1.52. So I still put 1.52, and then medium. The medium now I put 1.63. The medium now is 1.63. Then the rest is still the same lah. The R1 is still positive 20. R1 is still positive 20 because it is same side. The radius is same side as the reflected ray, whereas the R2 is negative because it's opposite side of the reflected ray. Okay, this is negative 20 centimeter. Be careful. Don't think that here the formula has a negative, then here you neglect putting a negative. So the R2 still has a own negative. This negative is from formula, and this negative is the R2 itself. So it's a different meaning. Yeah, these two negative has different meaning. This negative is from the formula originally. Yeah, this negative is from the formula originally is minus 1 over R2. So this negative is already there. And then R2 itself is also value negative. So there will be two negative. There will be two negative. Don't suddenly here got negative, so here you don't put negative, then it's wrong. Okay. Okay, now, so you see when you put it into a carbon disulfide, yeah, last time you put in the water. You see that? Last time you put in the water, now you put in the carbon disulfide. Different medium. Yeah, you put in first you put in water, now you put in the carbon disulfide. So the refractive index has changed. Last time is only 1.33, now it become 1.63. What is different is you can see that this value 1.52 over 1.33 is value less than 1. You see that? No, this is more than 1. This is more than 1. So when value more than 1 minus 1, you get a positive value here. This thing will become a positive value, isn't it? This value more than 1 minus 1, you get a positive value. Whereas this one is the value is less than 1. Okay, so when you value less than 1 minus 1, this part will become a negative value, isn't it? When this value lesser than 1 minus 1, of course here you get a negative value. So that's why this focal length suddenly become negative value. Yeah, let's check. Let's check. So okay, let's calculate. Let's calculate together. Let's calculate this part first. What do we get? 1.52 over 1.63 and minus 1. What do you get? Oh, I got negative. You see, I got negative value 11. And then this one is 1 over 20. And then here is still the same. Yeah, same like before. 20. This one negative become positive. Okay. And then what do you get for this one? Okay. So here 1 over 20 plus 1 over 20, so 2 over 20, and then multiply by negative 11 over 163. Yeah. Okay, so what answer do you get? Okay, so this is 1 over f. This is just 1 over f. 11 over 1630. Okay, so we need to take the reciprocal. Don't forget to take the reciprocal. So take the reciprocal. Okay, remember to take the reciprocal because it's just 1 over f. Be careful, be careful. Take the reciprocal. So so now after you take the reciprocal, you get what answer? I get the answer is, oh, I got negative value, negative 148.18 centimeter. So oh, now I got negative f. What does it mean by negative f? What does it mean by negative f? Negative f means it's a diverging lens. It's a diverging lens. Okay. So negative f is negative diverging lens. So it means a diverging lens. See that? This negative sign means diverging lens. Yeah. When f positive is converging, when f negative is diverging. So is it correct? Is it answer correct? Yeah, it's correct. Okay. So it's a negative 148.2, negative 148.18 centimeter. That's correct. Okay, that's correct. So you see, last time I did say converging lens must be convex, diverging lens must be concave. that's not always the case. Convex lens also can become diverging lens, not always become converging lens. You see, why convex lens can become diverging? It can become diverging if you put the convex lens into a very dense medium, very high refractive index medium, like carbon disulfide. This is very high, the medium, very high refractive index, very high refractive index, medium. Then you become 1.63. You see, very high refractive index medium. Refractive index is the n value lah. Very high refractive index medium. The convex lens, which is always normally convex lens, which is normally converging lens, suddenly can become diverging lens. The f become negative. You see, when you put the convex lens into a very high refractive index medium, it can become a diverging lens. You get f negative. But if you put in a less low refractive index, low refractive index medium, low refractive index medium, you still function as a converging lens. But if you put the convex lens into a very high refractive index medium, it can suddenly become diverging lens. So convex lens not always converging lens. It depends, yeah, where the lens is situated. Is it situated in a very high refractive index medium, or is it situated at a very low refractive index medium? So it can become diverging lens if you put the convex lens into a very high refractive index medium. Okay, so f positive is converging, f negative is diverging. So that's all for this video. So I hope you understand. Okay, that's all. And then don't forget about the how to get the positive R and negative R. Yeah, by comparing with the what? With the refracted ray. Okay, to compare with the radius. Okay, that's all for this video. Bye.